Jai Hind, dear students. Today I am going to teach a very important topic, wave optics of engineering physics. The subject code is BS 101. So today these are some references, textbook and reference book. The first book is a textbook of engineering physics by Navneet Gupta. Second one, textbook of optics by Ajay Ghatak. Third one, engineering physics by S.K. Gupta. Fourth, engineering physics by S.L. Gupta. And we can also refer this website for reference. So today we are going to cover basically introduction of the topic, introduction of the topic, then what is meaning of interference in brief, then types of interference, conditions for maxima and minima, coherent sources, methods to obtain coherent sources, and finally interference in uniform thin film. So today we are going to cover these 5 topics. So optics. So optics is the branch of physics in which we study about light or phenomena related to light. On the basis of dual nature of light, optics can be divided into 2 parts. So first one is geometrical optics, and another name is ray optics. In this optics, we consider that light travel in the form of ray. This also proves the particle nature of light. And second one, which is physical optics or wave optics, here we consider that light travel in the form of wave. This proves wave nature of light. So light is basically of dual nature. Sometimes it behaves like a particle and sometimes behaves like a wave. Interference. Basically, interference word comes when one thing interfere to another thing. Means for interference we need minimum 2 things or 2 waves. So due to superposition of 2 coherent light source, so minimum 2 coherent light waves of same frequency and nearly equal amplitude. The intensity of light is redistributed in space. This phenomena is known as interference. So basically interference is nothing but distribution of energy. So the intensity distribution at any point in space is the resultant of the individual intensity at that point. So interference means superposition of 2 waves. Types of interference: when 2 waves are superimposed in the same phase, that is, phase difference between them is integral multiple of 2 pi, or in terms of part difference it must be lambda. So 2 pi is equivalent to lambda part difference. Then constructive interference is produced. When 2 waves are superimposed in opposite phase, that is, phase difference between them is odd multiple of pi, then here pi is equivalent to lambda by 2. Then destructive interference is produced. So interference, in case of interference, 2 conditions are very important. One is when the path difference is integral multiple of lambda or phase difference is integral multiple of 2 pi. And in another case, path difference is odd integral multiple of lambda by 2 or odd integer multiple of or integer integral multiple of pi. So, these are two conditions and two cases, one is constructive interference, another is destructive interference. So, this is a diagram showing constructive interference and destructive. In construction, generally we get higher amplitude than initial waves, means amplitude is increasing, but in destructive amplitude is decreasing and it almost becomes 0. So, it is destructive interference. Now, conditions for interference. So, what are the main conditions for two waves to interfere to each other? So, we know that intensity due to superposition of two waves is given by. So, this is very general formula we study in 10+2 level. I is the resultant intensity, I1 is intensity of first wave, I2 is intensity of second wave, plus 2 under root I1 plus I2, under root is on both I1 and I2 into cos delta, where this delta is phase difference between two waves. It is phase difference. So, condition for constructive interference. So, as we have discussed, this phase difference must be integral multiple of 2 pi. So, better if we write delta is equal to n times 2 pi. So, here n must be 0, 1, 2, 3, so on and so forth. So, n could be 0, means n must be complete integer, either 0 or 1 or 2 or 3 or 4, like that. And in case of lambda, where we call it path difference, here you call it phase difference, that means in terms of angle, and this delta is known as path difference between two waves. It is also integral multiple of lambda, because this 2 pi is equivalent to lambda, because in complete oscillation 1 lambda in angle, this is 0, this is 180 and this is 360, means this is pi and this is 2 pi. So, lambda path is equivalent to 2 pi in angle. So, here condition is same, n is 0, 1, 2, 3, like this. So, if this delta is 0, we get constructive interference, means maxima. If this delta is lambda, we get again maxima. If this delta is 2 lambda, we get maxima. In similarly, in case of this delta, if this delta is 0, we get maxima or constructive interference. If this delta is 2 pi, we get again constructive interference, but order is changing. Here order is 0, 1, 2. Here order is 0, 1, 2. Now, condition for destructive interference. When phase difference delta is equal to 2n plus 1 pi, this 2n plus 1 is odd integer. If n is 0, this 2n plus 1 will be 1. If n is 1, then 2n plus 1 will be 3. If n is 2, 2n plus 1 will be 5. So, means this delta, if this is equal to pi, so we get first order destructive interference. If this equals to 3 pi, we get second order destructive interference. If this is equal to 5 pi, we get third order. Similarly, in case of path difference, so path difference must be equal to odd integral multiple of lambda by 2, because pi is equivalent to lambda by 2. So, if this path difference is equal to lambda by 2, so we get first order destructive interference. If this is 3 lambda by 2, second order, and 5 lambda by 2, we get third order destructive interference. Now, what is meaning of coherent source? Because for interference we need coherent sources. In our daily life we have so many light sources, but we are not observing interference like this tube lights, or in our daily life bulb etc. We are not getting any interference pattern. So, for interference we must have two coherent sources. So, first of all we try to understand what is meaning of coherent sources. Two sources are said to be coherent if they emit light waves of same frequency, first condition, nearly the same amplitude, second condition, and constant phase difference. This is actually must condition. If frequency is nearly same, it will doesn't matter. Similarly, if amplitude is nearly same, but phase difference must be constant. It cannot vary at all. If phase difference vary, then interference pattern will also vary. So, for interference of good contrast we need constant phase difference. So, this is essential condition. For the interference process, the coherent sources are essential. So, we have no choice. And what is meaning of incoherent sources? Two sources of light are said to be incoherent if the light they emit light waves whose phase changes with time. So, here in case of coherent sources, phase difference must be constant, and in case of incoherent sources phase changes with time, means phase difference vary with time. Now, methods of obtaining coherent sources in practice. So, there are two methods. One is division of wavefront, and second one is division of amplitude. In case of division of wavefront, the incident wavefront is divided into two parts. So, single wavefront gets divided into two parts. These two parts travel and superpose each other and produce interference pattern. An example of this type of division of wavefront method is Young's double slit experiment. We all are aware of this experiment. And another is Fresnel's biprism. Fresnel's biprism. So, here we have taken two examples. One is Young's double slit and another is Fresnel's biprism. So, now we see what is meaning of Young's double slit experiment. Here we can see that light source, from this light source these spherical waves are coming, these waves are coming, these are spherical waves, and we call this surface is wavefront. So, this single wavefront, if this wavefront reaches at this point, so this single wavefronts gets divided into two parts. One we call it slit S1 and another is we call it slit S2. So from single source we obtained two sources S1 and S2, both are perfectly coherent because they are part of same wavefront. So here we are dividing single wavefront into two. So this interference pattern is obtained by division of wavefront. So what we get? If you see, so here two types of waves are coming, and superposition between these two result into maxima minima, maxima minima, maxima minima. We call it fringe. We call it fringe. So maxima means where intensity is very high, or maximum, that is called maximum intensity. And another one is minima. Minima means intensity is very low or almost zero. So minimum intensity means zero intensity, a maximum intensity means maximum intensity available. Another example or another method of obtaining coherent sources is by division of amplitude. In first one we have divided this wavefront, and in this case this we try to divide amplitude. So let us see how. The intensity of the incident light is divided into two parts. Intensity means amplitude, because intensity is nothing but a square of amplitude. So either we call it amplitude or intensity. These light beams superimpose afterwards and produce interference pattern. An example of this kind of division of amplitude method is Newton's rings, and another is Michelson interferometer. So again we have taken two examples, one is Newton's ring and Michelson interferometer, and also thin film interference, that is today's topic. So interference by division of amplitude. So this is famous Newton's ring experiment, and this is Newton's ring obtained by white light. So the center is dark. So this maxima, this white portion is maxima, then minima, maxima, minima. These circular rings are known as Newton's ring. So this type of interference we are getting is by the division of amplitude. Conditions for sustained interference. So what are the essential or main conditions to obtain sustained? Sustained means the pattern does not change with time, that means sustained. To obtain a clear and stable interference pattern, following conditions must be fulfilled. So these conditions must be fulfilled to obtain sustained interference. The first condition is the light source must be monochromatic. So what is meaning of monochromatic? So light must be monochromatic. Monochromatic means single wavelength, a fixed wavelength, or fixed frequency, or single frequency, or single wavelength. That is, the wavelength or frequency of wave must be same or unique. The light source, second one is the light source must be coherent. As we have discussed earlier, light source must be coherent. Coherent means phase difference must be constant. The third one is the amplitude of the both waves must be nearly equal for good contrast. If we want to see very clear this maxima and minima, so the amplitude should be nearly equal. So contrast will be good. The wave must, this fourth one is, the wave must propagate in same direction. So this is obvious. If waves are going here and there, we cannot observe interference. Interference means they are propagating in same direction. So these four conditions must be fulfilled to obtain sustained interference. Now, this is our today's topic, interference in uniform thin films. So we are going to discuss in detail how, due to uniform thin film, this interference pattern is obtained. So a film is said to be thin when its thickness is about the order of wavelength of visible light. So what is meaning of this thin film? Thin film means its thickness must be of the order of wavelength of visible light. So visible light is 4000 angstrom to nearly 8000 angstrom. So 0.4 micrometer to 0.8 micrometer. So if a film has this much thickness, then this film will be known as thin film. A thin sheet of transparent material such as glass, mica, etc. are treated as thin film, right? So glass, mica, etc. are thin film. When a thin film of oil is spreads on the surface of water and exposed to white light, beautiful colors are seen. When we wash our clothes, sometimes we observe some colorful bubbles. So these bubbles, colorful bubbles, are nothing but interference pattern obtained in thin show film. Similarly, color phenomena is observed when a show film, yes, this show film illuminated with white light. So we observe so many colors because of interference pattern. Example, a thin film of oil on the surface of water, thin film of soap bubble, these are the example of thin film interference. So this is the diagram in which we will study the thin film interference. So this thickness T from here to here, this is thin film in consideration. Its thickness is T, and we are knowing that T must be of the order of 0.4 micrometer to 0.8 micrometer. This thickness must be around 0.4 micrometer to 0.8 micrometer or something more or less, and its refractive index is mu. So consider a parallel transparent thin film of thickness T and refractive index mu. Mu must be greater than 1. 1 is the refractive index of air. So thickness, this refractive index must be greater than 1. A ray of monochromatic light AB is incident at an angle I. So I is angle of incidence, is partly reflected and partly refracted. So this AB is incoming wave, AB incident on this thin film, and one portion is reflected in direction R1. So this is reflected rays. Another portion is transmitted in film, that is BC. So from C it emerges or transmitted in direction T1. So T1 is transmitted rays or wave, and CD is this BC and CD, it is multiple reflection in thin film itself. So BC is the ray in thin film and CD also in thin film, and after D again it emerges as R2. So R1 and R2 are known as reflected rays. T1 and T2 are known as transmitted waves or rays. So if we try to study the interference between these R1 and R2, it is known as interference in reflected system. So if we study interference between this R1 and R2, so this kind of interference pattern are known as interference in reflected system or in reflected waves. And similarly we can study interference in T1 and T2. So this is interference in transmitted wave. So basically we have two cases, one interference in reflected waves and interference in transmitted waves, and this I is angle of incidence, and this is normal at point B, and this is angle of refraction R. So this is angle of refraction I, and angle of incidence I, and R is angle of refraction. The refracted ray travels in the film and reaches the lower surface, right? Again it is partly reflected and partly transmitted. This way light undergoes through multiple reflection. So we have taken only two, this one reflection, this another, then it goes on like this. So through this multiple reflection, amplitude of waves is dividing. That's why this type of interference is known as interference due to division of amplitude. So first of all we will consider reflected system. The reflected set of beams, that is R1 and R2, come from coherent sources, so they will interfere. Why they are coherent, R1 R2? Because both are coming from single rays AB, A to B. This single ray AB gets divided into R1 and R2, T1 and T2. So they will interfere. The part difference between them is given by, so part difference, how we will calculate part difference? Part travel by R2, part travel by R1. That is meaning of difference. Part travel by R2 minus part travel by R1 is the part difference between R1 and R2. So part difference we represent by this delta or triangle BC plus CD. If you see BC plus CD, if you see from here, this perpendicular up to here part difference same. If we are looking from here, so N and D both are at same distance. From D, this BC plus CD is extra path covered by ray R2, and NB is covered by R1. That's why this part difference is BC plus CD minus BN. BN is multiplied by 1. Why? Because BN is in air. So BN here medium is air, and here BC and CD are in thin film mu. So, according to Fermat's principle, to nullify we have to multiply refractive index by refractive index mu. That is why this mu, because optically these two medium are different. So, mu times BC plus CD is path travelled by R2 and Bn into 1 path travelled by R1. So, this is equation number 1. In triangle BCM, BCM, so this is right angle triangle. So, this is angle BMC is right angle. So, in this triangle, and second triangle is BCD, MCD. So, we have taken two triangles BMC and MCD. So, BC plus CD both are equal. So, this is equal to Cm by cos R, and Cm is nothing but thickness of the film T. So, T by cos R. So, this is equation number 2. Similarly, Bn is equal to Bd sin I. So, Bd is nothing but Bm plus Md sin I, and Bm is Cm tan R and Md is Cm tan R into sin I. So, Cm is T. So, 2T tan R sin I. So, this is equation number 3. Also from Snell's law, mu is equal to sin I by sin R. So, Bn is equal to 2 mu T sin square R divided by cos R. So, this is equation number 4. So, part difference delta is equal to 2 mu T cos R minus 2 mu T sin square R divided by cos R. So, if you solve by simple algebra, so get part difference 2 mu T 1 minus sin square R divided by cos R. 1 minus sin square R is cos R, cos square R. So, cos square R get cancelled by cos R. So, we get finally part difference is equal to 2 mu T cos R, which is equation number 5. So, this is part difference between ray R1 and R2, which is 2 mu T cos R. The reflected system R1, the reflected beam R1 is reflected from the denser medium at B. Therefore, there occurs an additional part difference of lambda by 2 or phase change of pi. So, when any waves gets reflected from rare to denser medium, then a sudden change of pi, phase change of pi or part difference of lambda by 2 occurs. By the Stokes theorem, we can understand according to Stokes theorem. So, effective part difference will be 2 mu T cos R plus minus lambda by 2. So, now condition for maxima and minima, we are knowing that maxima or bright bands. So, 2 mu T cos R plus minus lambda by 2 must be equal to n lambda. So, 2 mu T cos R is equal to 2n plus minus 1 into lambda by 2. So, equation 6 is a condition for maxima, or n will start from 0, 1, 2, 3. For plus sign 1, 2, 3 and 1, 2, 3 for minus sign. Whatever option we can explore, both are correct. Similarly, for minima or dark band, so here this part difference must be equal to odd integral multiple of lambda by 2. So, final condition is 2 mu T cos R is equal to n lambda, where n is equal to 0, 1, 2, 3. So, here we are going to stop. Jai Hind, dear students, thank you so much.